vector rate lambda r. Finally, you've got the recovereds categorized in R. So these are people who had the disease. They're either recovered, so they're better and they're immune, they can't get it back, or they're removed, in which case they might be quarantined or they might be permanently removed from the population. And when you integrate your equations, you see the lovely curves we have on the right. So the green bar there is your susceptibles, and you see in the beginning almost everyone is susceptible. You have a small seeding of infected individuals, and they're tracked via the red curve. So you see that the red curve peaks at about 0.4 in this particular instance, and then goes away. And in the long time limit, you've only got recovered individuals left in your population. But there's a pretty big problem with this model. It works quite nicely in a homogeneous setting. So it was tested, for example, on like a boarding school in the UK back in the 20s. But it doesn't allow for any structure of your population. And as we know, populations are structured, right? I'm more likely to meet up with people in Limerick than I am to meet up with people in Donegal or France, for example. So there's structure in your population and there's a little bit of nuance there. So how we deal with that is we deal with it with networks. And I know that Joey and Kleber gave 2 great talks about networks, and I'm sorry for throwing more of them at you. But just to give you some examples of what I'm talking about, on the left, I've got a network of a zebra herd. So each red dot there in your network is a zebra, and the lines connecting them are interactions between the zebras. And what I like about this network is you've got this kind of this core component where there's a lot of connections between individuals. So on the left, you've got this deep cluster. They're all connected. And then you've got on the outside, you've got these peripheries, these cliques, and they're a bit further away. On the right, this is a recent work. One of my other collaborators, Project McCarran from UL, he also worked on this. So this is the network in A Song of Ice and Fire. So these are interactions between all the characters from the Game of Thrones series. A couple other examples, I suppose on the left, this is a more matchy example. It's what we call an Ehlers-Danlos graph. So it's a fully random network. You throw all your nodes on a page and you just randomly start throwing edges around the place. So everything is completely randomly connected. I mostly have been using these because I'm not overly interested in the exact structure, more of the general network setting. And on the right, we've got a road network. So in this case, your edges are the roads, and where the roads meet, say in a crossroads or a town or a city, those in this case are your nodes. So what I'm really trying to get at this is that nodes, oftentimes they can be represented as individuals, but they don't have to be individuals. You can look at all kinds of different scales. You could call each node, say, a household. You could look at each node being like a town or a city or even a county or a country if you wanted to. So there's lots of different scales. And we're kind of looking in a general way at what we call a meta-population network. So each node has got a certain population of individuals and a carrying capacity. So there's a limit on how many individuals can be on that node at any one time. So what do we do? Oh, I'll just talk about a few more things. Just 3 really important matrices in networks theory, although some of them have already been explained to you earlier. So the first one is the adjacency matrix. So it's an n by n matrix where n is your number of nodes. Aij is 1 if there's a connection between node I and node j. It's 0 otherwise. You've got your degree vector k. So that's just the amount of edges. So ki is the amount of edges coming out of node I. And last, but most importantly, we've got the Laplacian. So this models diffusion in your network. So it allows individuals to move from node to node. And it's your adjacency matrix divided by the degree minus a Kronecker delta. So your Kronecker delta is 1 if I is equal to j and is 0 otherwise. And on the right, I've got a pictorial representation of the adjacency matrix of our zebra herd in the beginning. So you can see in the upper left, that's that really densely connected little cluster. And then towards the bottom right, you'll start to see a couple of these little cliques. Okay, so let's put the SIR model on a meta-population network. And there's 2 mechanisms going on here. You've got the reactions within your node, and those are your disease spread reactions. And then you've got your diffusion mechanism, and this is allowing individuals to travel through the network. And that's how also, incidentally, how the disease spreads through the network, because it can completely rampage in a single node, but how it gets out of that node, it does that through diffusion. So that's what these DLs are. D is a diffusion constant. I usually just set it equal to 1, and L is your Laplacian. And if you look on the right, I've got this totally not confusing diagram. Each line is the population on a node, or rather the proportion that it's filled. So in the beginning, I give each node is half full, so it's got a population of 0.5. And as time goes on, you'll notice that there's this stratification. So in the long-term limit, you've got a whole bunch of, you've got some nodes that have a population almost at 0.6, a couple that are almost down at 0.4. And what this is representative of is the degrees. So your normal bog standard Laplacian is a random walk Laplacian. So I'm not paying attention to which node I'm going to. I'm just bouncing around the network randomly. And so I'm obviously more likely to end up at a node of a high degree than of a low degree. And that's why we see this stratification. Okay, let's take a look now at what happens if we change the speed of the reaction rates relative to the diffusion rates. So what I'm going to do is I'm going to make my lambda I be really, really big. I'm going to make lambda R be 1/10 of lambda I, so the recovery rate will always be slower than the infection rate. I'm just going to leave my diffusion as 1. And I'm going to test that out for different ratios of reaction rates to diffusion. And what's really cool, actually, is that if the infection rate of your disease is low, then the peak of your infection, so those infection curves I showed earlier, is much higher. So what's happening in this case is that because the diffusion is able to keep up with the infection reactions, it's able to spread at the same, it's able to move people around the network at the same sort of rate that people are getting infected. But if people get infected and thus recover much more quickly than they can diffuse through the network, then the infection peak is much lower. So if you look at the bottom right, the reaction, so the infection recovery rate is 100 times quicker, relatively quicker than the diffusion. And so your peak is way lower. So that would be quite nice to get, because we want to, I remember back in March and April when we were introducing lockdown, everyone was saying we have to flatten the curve. So this is one way to flatten the curve, but unfortunately, we can't really change the timescales that the disease works on, and we also can't really change the timescale that a human being works on. You know, you have to go to the supermarket once a week. You have to go to work Monday to Friday. So we can't change those timescales. But what we can try to do is introduce this idea of social distancing. So what we do is we model our Laplacians, or we don't model, we modify our Laplacians. So we take the usual original random walk Laplacian, and now we add these extra terms in. So I'm not sure if you guys can see my mouse moving around the screen, but it's the Sj times the 1 minus Si minus Ii minus Ri all to the power of sigma. So that's these terms here. And what's happening is that we're modeling the rate at which an individual is jumping from node J to node I. And this individual is looking at the amount of empty space there is in node I. And we raise that to the power of sigma. So if sigma is really high, then we're going to be really, really careful about going to nodes where there's already a lot of people in. And if sigma is low, or even if it's less than 1, then we're going to start jumping towards nodes where there already is a lot of people. And then the Laplacian has to be balanced. So diffusion is a two-way system. So we've got the reverse here on the right. And we model that for, we have one Laplacian for the susceptibles, one Laplacian for the infected, one Laplacian for the recovered. So again, the higher sigma is, the less likely individuals are to congregate at busy nodes, and the more likely they want to stay in their less busy nodes, so the more likely they are to stay where they are. So let's take a look at some infection curves, right? I have sigma equals 0, so we've got absolutely no social distancing going on whatsoever. And I've got sigma is equal to 5. And what you can see in the blue curve is that the peak happens both or the peak is the proportion of your population that's infected. And the peak of the blue curve, it happens later and it's lower in the case where there's social distancing. Okay, what happens if we go for some really more extreme social distancing? What if I set sigma equal to 15? Now we're starting to see what looks like multiple peaks. So let's push it up all the way to sigma is equal to 30. And now we start to very clearly see second waves happening. So what's happening here is that the disease is spreading within nodes, but it's really struggling to break out of these. And each peak is is giving us information that of the path length. So that second peak that you see, those are nodes which would be a distance 2 away from your original seed nodes. The third peak would be nodes that are a distance 3 away from your original seed nodes. And so by changing the behavior of the individuals, not changing the reaction rate and not necessarily changing the diffusion rate either, but trying to influence people's behavior, it almost looks as if second waves are kind of inevitable in this setting. But what is important to note is that ultimately your peak is lower in the cases where you have a higher social distancing. And this is really, really important for your healthcare systems. Okay, but what about if, before I go on to that, there is no such thing, of course, as a free lunch. So I think Joey, or maybe it was Kleber earlier on today, he mentioned this idea of entropy. So it's borrowed from information theory, and I'm not really going to go into it too deeply, but it measures the mobility that individuals have. So it measures their ability to explore your network. So what I've done here is I've plotted 3 curves with so in the blue curve, I've got an average population initially of 0.3 per node. With the red curve, 0.5. With the orange curve, I have an average population of 0.7 per node. And then I'm increasing sigma and I'm trying to measure my entropy. And you can see that it definitely tails off quite quickly. So unfortunately, there's no such thing as a free lunch. We can't just massively increase the sigma without paying a cost. And how we balance that, I guess, is more up to policymakers than it is up to us. But what about this idea of restlessness? So what if, right, instead of going out every single day but being careful, what if I only go out once every 2 weeks, but when I go out and I leave my home, I'm not at all careful. I'm going to just, I don't know, go to the pub or something. So now I've added in red another set of terms to my Laplacians. So these are Sj plus Ij plus Rj. So I look at the amount of individuals that are in my current node and I raise that to the power of gamma. So gamma being less than 1 means that I'm going to jump around more. Gamma being greater than 1 means I'm going to try and stay at home. But this is influenced by the population that is already on my node. So if there is a high density of people where I currently am, I am more encouraged to leave node J, where I currently am. Of course, that also depends on how much empty space is in the node that I'd like to go to. And again, we have to balance the Laplacian because diffusion is a 2-way street. And what happens if we just stay home, but not care about what happens when we go out? Well, similar stuff. Going out less also definitely makes a difference. Well, so what I've done here is I've plotted 3 infection curves for gamma equals 0. So that's gamma is 0, sigma is 0. I've plotted sigma is 0, gamma is 5, sigma is 0, gamma is 15 in the orange, and sigma is 0, gamma is 30 in the green. And again, staying home a lot, as much as possible, also affects the infection curve. So it's not necessarily enough always to just go out regularly, but going out carefully. Staying home also has a really, really big impact. And what's cool about this, we have this parameter sigma and we have the parameter gamma. So we've got these 2 free variables in our system. And we've got a measure for the mobility of our network, the entropy. So what we can do is we can try and balance the restlessness and the crowding effect. So to keep a constant entropy. And we find there's this linear relationship between gamma and sigma for a constant entropy. And what's also really cool is that as long as you keep your entropy constant, then the ratio between sigma and gamma doesn't really have a huge impact on the infection curves. That's why this slide doesn't have any infection curves. They're all the same, so long as you're keeping your entropy constant. So then that's basically the end. So in conclusion, we've got this meta-population SIR model, and we introduced this idea of crowding, so this idea of social distancing, and it seems to work. It seems to flatten infection curves, which is great. It also seems to make second waves almost inevitable, but it all comes at the cost of entropy. Reducing mobility, so reducing restlessness and staying home as much as possible, can have a similar effect, and how we balance the two, I guess, really is key ultimately. So thank you very much. If you have any questions, I'm more than happy to take them.